In the previous lesson, I introduced the concept of I/O model, which is an abstract model that we can use to analyze the I/O behavior of an algorithm. In this lesson, we're going to see how this analysis of the I/O behavior actually works. But before we get to this example, let's have a look at our model again. So the model has an external memory, or disk as I often call it, and an internal memory, and a CPU that actually performs the computations. Now, when the CPU or the algorithm needs a particular data element which is stored on disk, then it needs to read that data element into the internal memory. And it's going to do that not by just reading a single item, a single element, but it's going to read a full block of elements. Okay, and the important parameters of the model are B, which is the size of such a block. How many elements do you actually get when you read a block? Okay, and M, the size of the internal memory. Okay, and size, again, is not measured in megabytes or something, but in the number of elements. Okay, so this is our basic model. So how do algorithms in this model work? Well, as I already noted, the CPU can only work on items that are in the internal memory. So what does it mean? If it wants to do a computation, like add some data element to some number or something, then if the element is already present in the internal memory, the computation can just go ahead. If it's not, then actually first the data element has to be read from the disk into the internal memory. Okay, and remember that the way this is done is not by reading a single element, but by reading a block. And it's important to realize that the whole point of analyzing things like this is when the data is so large that it does not fit completely into the internal memory. So what's going to happen at some point during your computation, that maybe you want to read a block because you need a certain element from that block, but that your internal memory is already full with lots of other blocks that you've been reading. When that happens, before you can read the new block, you actually first have to write some of the blocks that are currently in your internal memory. Out of those blocks, you have to write one back to the disk. Okay, and the analysis that we want to do is how many such I/O operations, so either reading a block or writing a block back to the external memory, how many such I/O operations our algorithm does. Okay, so let's have a look at an example. Okay, remember that the example we saw before was that we have, let's say, a three-dimensional model of the Alps, for instance. And this model is in the form of a two-dimensional array, where for each cell, which roughly corresponds, let's say, to a 1 by 1 meter area in the Alps, for each cell you know the elevation at that particular point. Okay, so we have a two-dimensional array, which is huge, because the Alps are a huge area, and we now want to compute the average of the values stored in this array. Okay, and because the Alps are so large, this data is so large, this array does not fit into the internal memory of your computer. Okay, so how can we compute the average value? Well, it's very simple. We simply go over all the elements in the array, add their values, and then take the average. The number of I/Os that is performed, however, depends on the way in which this array is stored in blocks. Or more precisely, which elements are stored together in a block. How this is done, which elements are put together, is determined by what is called the blocking strategy. And for two-dimensional arrays, a standard strategy would be that blocks are formed in what is called row major order. So you simply go over the array row by row and form blocks in that way. So for instance, if b equals 3, right, so 3 data items fit into one block, and remember this 3 is not a realistic value. In practice, b would be several hundreds or maybe thousands. Okay, but if B is 3, which is easier to show in this example, then this would be the first block, right? The first 3 elements of the first row. The second block would be the second 3 elements, and so on. This will be another block, and this is the way it's stored. Okay. So let's see what the algorithm is doing. So we have an algorithm that goes over the items row by row. Okay, so here's the algorithm, and it goes over the array in this order. So let's see how many IOs it's going to do. Well, remember that as soon as the algorithm needs to access a certain array element, so say aij, well, it's first going to look for that element in the internal memory. If it's already there, fine, the computation can proceed. If it's not there, then we need to read this element. And actually what we're going to get is the block containing that element. We need to read that from the external memory. Okay, let's have a look at how this works. And let's assume that here M, the size of the internal memory, is 15. And again, in practice, M would of course be much larger, let's say several millions. But for illustration purposes, it's nice to look at a small example. Okay, so how does it work? Well, the algorithm first reads the data element from the top left corner. Well, initially everything is stored on disk, so it's going to need to read this particular block. Okay, it reads the block and it adds the value to our sum. Then it goes to the next element, and this is nice because this block actually is already in the internal memory because we just read it. So we can proceed without reading a new block. And also for the third one, we can simply add its value and we don't have to read the block. When we get to the next element in this row, however, the block is not present, right? We go to a new block, and so now we need to read this particular block. Okay, we can add the value, continue, go to the next one, well, not present, read the new block, go to the next one, and so on. Okay, so this is the way it works, until at some point the following happens. We want to read a new block, but the internal memory is full. Right? In this particular example, we had b equals 3, m equals 15. So that means that the internal memory can hold 5 blocks, and we already have 5 blocks in internal memory. So at this point, we cannot read a new block before we throw out or write back to disk one of the old blocks. Okay, so what we must do is we must, what is often called, evict a block from the internal memory, write it back to the disk. Okay, and now the question is, which block do we decide to write back to disk? Well, this is determined by what is called the replacement policy. Okay, which block do we use to replace the new one? Well, a standard policy is LRU, or least recently used. So that simply looks at the block that we did not use for the longest time, and that one is being written back to disk to make space for the new block. Okay, so if we run our algorithm with b equals 3, m equals 15, and least recently used, then what's going to happen at this point in time is that the first block that we used, that's the one we have not used for the longest time, that one is going to be written back to disk. Okay, so now we have 4 blocks, so we have space for a new block, and we read a new block. Okay, we use the next element, and then we get here. Well, again, we need a new block, but we have 5 blocks in our internal memory, so it's full. So we need to evict a block. Well, least recently used would evict this block, and so on. Okay, so this is the way the algorithm works. Now let's have a look at the number of IOs. Okay, so it's easy to see that this algorithm is going to read every block only once. Right? When we read it, we use the first element from the block, then the next ones, and so on. And then when we go to the next block, we will never use this block again. Okay, so each block is read only once. Well, the number of blocks, how many blocks do we have? Well, if we have n elements in total, so we have, let's say, an m by m array, and n is m squared, so the total number of things in our two-dimensional array, then if b of the elements fit into one block, then we have n divided by b number of blocks. So the number of reads that we do is n divided by b. And actually we also have to count the number of times we write something back, but again, every block, once it's written back to the external memory, we don't need it anymore, so it's also written at most once. So the total number of IOs is at most 2 times n over b, so order n over b. That's pretty nice. In the next lesson, we're going to look at how the column-by-column algorithm does. And what we'll see is that it indeed is going to do many more IOs.